Okay, now we're ready to talk about the law of total probability. In fact, this result we have most recently used in the box containing 8 white balls and 4 black ones. If you remember, when we were trying to find the probability of getting black in draw 2, we were trying to figure out what the first draw would be, whether it's white or black. And then we're using the conditional probability together with the multiplication rule. But finally, we add two things together in order to get the marginal probability of B2. Okay, so back there, we talked about that result. And here we're formally introducing this law of total probability that could be really useful in many situations. So we're considering events A1 through AN, they're disjoint. Okay, so remember when they're disjoint, they're mutually exclusive. Okay, no two can happen at the same time. Moreover, they are exhausting the entire sample space. Okay, so if you look at this notation, now we know the union of all of the AIs, okay, is the sample space. Okay, so what this tells us is that once we have this condition met for any event B, the law of total probability goes this way. Okay, the marginal probability of B is the conditional of B given A1 multiplies with marginal of A1. Okay, and we know from the multiplication rule, this becomes B intercept with A1. Okay, and then similarly, this term is B intercept with AN. Okay, and what we're doing here is that we're breaking the marginal probability of B into n different pieces, where each piece is the intersection of B with a particular AI from the definition that we defined earlier about the disjoint events as well as exhausting the entire sample space. Okay. Once we have this set up, we're going to call this sets A1 through AN. Okay. We're also going to call it as a partition of sample space. Okay. And what this means, so the entire definition that we did up here means that A1 through AN, it's a partition. Okay, they're disjoint, but at the same time, they exhaust the entire sample space S. So mathematically, hopefully this starts to make sense, okay? But I would also like to take the chance to talk about it, how to understand it in a graphical way, okay? So remember, we always like using a big box as the sample space, okay? And in order to represent A1 through AN here, one way we can do it, remember they're disjoint, okay? But at the same time, they exhaust the entire sample space, meaning that the union of all of them is the sample space. So we can just, I'm doing this arbitrarily now, okay? So like say here, let's just say this is A1, A2, A3, A4. Let me just use 5 as an example, okay? But n is an arbitrary number. So what I'm doing here is that I'm showing A1 through A5, okay? They're disjoint, right? Like no intersection with any of the two. And then they are also like in this definition, like we call it the partition, because they're not only disjoint, but they exhaust the sample space, okay? So once we have done this, let me just use a different color to show B here, okay? So B, okay, we're talking about marginal probability of B, okay? And you see that here, we're looking at the intersection of B with any of the A, and then we are adding it up, okay? So let me just try to figure out a B that actually intersect with all of them, just to give you a sense. But just say this not really well drawn circle is B, okay? So if we focus on this B, okay, we know that whatever goes into this area, this blue area, is the marginal probability of B, okay? But look how we can come up with that when we're looking at the intersection of B with each of the A's. So this, okay, this part is our A1 intersect with B, okay? This is our A2 intersect with B, okay? This is our A3 intersection with B, A4, intersect with B, and then A5, okay? So when I do it this way, hopefully visually, you start to see that, well, indeed, the marginal probability of B is the adjoint probability of B with all of the A's separately, okay? And we add things up together, okay? Lastly, as you can see here, Yes, we know that it's going to be the joint of B and A1, but maybe more commonly, in order to get that, you're going to use the multiplication rule where you know the margin of A1, and then you also know the condition of B given A1. Okay, so that's a breakdown of the law of total probability. And hopefully it starts to make sense, not only mathematically as well as visually. And now we can talk about an example before we end this part. Okay, it's a little bit long, so just bear with me. A firm is considering a drug testing program for its employees. Before it begins, the firm wants to know the scope of the problem, if any exists. Okay, realizing the sensitivity of this issue, meaning that, well, you might not be able to ask directly whether you are taking any drugs. The personnel director decides to use a randomized response survey. Okay, we're going to explain what that is. It is believed that respondents are more likely to be honest when such forms are used. All right, so how it goes. Each employee is asked to flip a fair coin, okay, heads or tails. If the coin comes up heads, answer the question, do you carpool to work? If the coin comes up tails, answer the question, have you used illegal drugs within the last month? Assume that all employees answer the survey honestly. Let's look at those numbers here. Out of 8,000 responses, 1,420 answered yes. Okay, so again, we don't know whether it's yes to each of the question, okay, but we know the total number of yeses is 1,420. Suppose the firm knows that 35% of its employees carpool to work. What is the probability that an employee chosen at random used illegal drugs within the last month? Okay, so it is a pretty wordy question, but I think overall pretty interesting, and you get a chance to see how randomized response survey work, and maybe in the future you might want to use it for your own study one way or another. Just like a lot of the examples that we have seen before, it is pretty important to set up the problem in a probabilistic way. Okay, what I mean by that is here we know that this is trying to use the law of total probability, okay, the concept that we just covered. So we might want to figure out what is our A, like how many A's are there? We know generically is A1 through AN, but then how many are we here? And then also what is the event B, okay? So to get us started, I'm gonna define that for all of us, okay? Let events A1 to be the coin comes up with head, A2 comes up with head with tail, and then B is the answer yes. Okay, so now you see, well, we do know the marginal of B, right? It's 40/20 over 8,000. So we do know PB, okay? And we also know that, well, A1 and A2, they're a partition because they exhaust the entire sample space when you're flipping a coin. So once we set it up here, you see that we're able to use the total law of probability. Okay, and we do know, let me write it out for us, that given what we know so far, it's gonna be PB is the sum of B given A1, okay, times A1 plus probability of B given A2 times the margin of A2, okay? All right, so what I want you to think about is, of course, we actually, in this case, we're not trying to get PB, we know PB, okay? Like we said, is 1420 divided by 8,000, okay? And we also know PA, okay? PA1, PA2, because it's a fair coin, so each of this is 0.5, okay? And lastly, if we, let's see, we answer, we defined, so if the coin comes up head, answer the question, do you carpool? Okay, and we know that what is 35% of its employees carpools. Okay, so this conditional probability, okay, is that if I randomly select a person who is supposed to answer the first question, then this conditional probability is going to be 0.35. Okay, and of course, like I said, this up front is 1420 divided by 8,000. Okay, so now we have one equation, right? We have 1, 2, 3, 4, 5 terms, and we have 4 of them known. This is the only unknown that we're trying to solve. So this now becomes a algebra problem. Okay, so let me show you the entire answer here. Okay, just like what I talked about, yes, we are using the law of total probability here, but it's not a direct application. Usually like in the, like what we saw, like when we see it, it might be that, oh, I know this conditional, this marginal, this conditional, this marginal, so we're able to get this marginal of the other event. But in this application, you see that we're also able to use this in an indirect way to solve the unknown of this, in this case, a marginal conditional probability of getting drug. Okay, so that's the thing. So notice that here we're using P carpool and P drug. Okay, but they are really, given the question is the conditional probability given whatever your the outcome of the coin flip comes up, but at the same time they are marginal in their own sense. Okay, because well, once we know which which side of the coin comes up, we know that this becomes a marginal probability among all of the people who actually are supposed to answer the first question. Then we know it's probably of couple, and then among all of the people who are supposed to answer the question of the second question, then that will become our marginal as well. Okay? So hopefully this gives you a good exercise to think about how we can use the law of total probability as well. There are many different ways that you can use it depending on the task that you're supposed to solve. Okay, so to recap, okay, we define marginal probability, okay, joint probability, and then of course the conditional probability, where here the PB needs to be greater than 0. Okay, the multiplication rules told us that we can always, from the conditional probability and the marginal, conditional probability and the marginal, that we're able to get the joint of A and B, or A intercept with B. And lastly, to generalize it to some degree, we're able to produce this law of total probability for a partition, that we're able to get the marginal of B as the sum of the joint of B and all of the partition elements of AJ or AI.